Okay. So for homeostasis, by definition, is the body's ability to maintain a constant internal environment, certain variable that could be temperature, pressure, pH, regardless. Um, Constant internal environment, regardless of external conditions. So even with changing external conditions, the body can maintain a consistent internal environment. Um, so for example, if we have a graph with, I almost wrote temperature there, temperature and time, this variable right here being temperature on the y-axis, and on the x-axis we have time. A graph of a person's temperature over a 14-hour period may look something like this, and that is completely normal. And um, this right here, this range that their temperature is in, is called the normal range. Somewhere between about 96 and 98 degrees is normal range. And then for them, that average of their normal range is called set point. And set point is what their body is trying to maintain through homeostasis. That's their consistent internal environment that their body wants to maintain. Their body maintains this using a reflex control pathway. Um, and reflex control pathways have several components, starting with a stimulus. I'm going to use the temperature control pathway to describe this just because I already have been describing temperature. So let's say that the stimulus is a decrease in temperature. It's a really cold day outside. It's like -10, like it is in Rexburg sometimes in the winter. And so somebody walked outside and it's -10 degrees outside, and so the stimulus is taken in by a receptor, and that receptor could be a receptor in their skin cell. And that receptor is going to send a signal to the control center, which in this case is their brain, um, through an afferent pathway. Now, the afferent pathway could be in a reflex control pathway. It could be neurons or it could be through the blood. In this particular pathway, it is a neuron. Then the control center is going to decide what to do. It processes the information, processes info, and then it sends a signal. It sends out the decision, right? So the control center is going to send out the decision through an efferent pathway. Now this pathway also could be neurons or the blood. In this case, it is also neurons. Um, this temperature pathway. In other pathways, it's not always neurons. Hmm. Then, once that control center sends out a pathway, they send it to the effector. And the effector is the thing that's going to affect the stimulus. So the effector sends a response to the stimulus, and the stimulus is affected. And either the stimulus is amplified or it's brought down. And so this right here in blue that I'm going to draw, this part of the pathway from the receptor to the effector, we call a feedback loop. The part that doesn't control or that doesn't contain the stimulus, because the stimulus kind of controls this feedback loop. There's two kinds of feedback, the negative feedback loop and the positive feedback loop. And the negative feedback loop brings things back towards the set point. Um, an example of a negative feedback loop is the temperature regulation, like this up here. This is negative feedback. See how it's bringing it towards set point up here? So temperature regulation is an example. Another regulation example could be pH regulation or blood glucose regulation. An example or positive feedback, sorry, takes things away from set point. So it takes away from set point. And there are really only two examples in the body where positive feedback happens on purpose or happens for a good reason. And one is child labor. And the pressure on the cervix is the stimulus, and it causes a feedback loop that then causes more pressure on the cervix. And then that happens over and over again until the child is expelled. And then you've experienced child labor. And then the other one is lactation. And when the child latches, then that causes a feedback loop. That is a positive feedback loop. So then it causes more production of milk. Another example that could be positive feedback is like if we took this graph right here and we just went like this and we never came back. That's positive feedback. It's taking it away from the set point. However, if you had like a fever, um, there is a chemical that's released that actually raises your set point so that having a fever is a negative feedback loop. So having a fever is an example of negative feedback. So when you're sick and you have a fever, that's an example of negative feedback. All right, so for transport, we're going through three different kinds of mediated transport or protein-mediated transport. So the first kind is diffusion through channels, so channel-mediated transport. And there are a few kinds of channel mediate or channels that we can use to mediate transport. The first one is a leakage channel. And in a leakage channel, this opens randomly, so it randomly opens and closes. It's very molecule specific. And usually the way that these are molecule specific is they have a sphere of hydration around them, and it uses the size of the molecule, the polarity of the molecule, the charge of the molecule to recognize and only let those ions or molecules through. So a leakage channel is very molecule specific. One that's really important to us in physiology is the potassium leakage channel. These also, we call them pores. The next one is a voltage gated channel. And voltage gated channels are opened by electric potentials. Ooh, or electrochemical potentials. So usually we have, one side of the cell is positive, one side of the cell is negative. If that changes or one side becomes more negative, then that will open the channel. And then there's a channel there. A lot of the things that we talk about in this class are voltage gated channels. The next one that we talk about are chemically gated channels. So chemically gated. These are also called ligand gated channels. That's just because they are opened by small molecules. Molecules. Usually like hormones or neurotransmitters that bind to receptors in the channel. So an example of this would be acetylcholine. And then the last one is mechanically gated channels. And this opens when there's a change in like the membrane. So the membrane is actually manipulated. So I'm going to say opens when there's a manipulation of the membrane. There is a physical manipulation of the membrane. Like there's pressure or there's a temperature change or it's being stretched or pulled or pushed. That will open a mechanically gated channel. So that's channel mediated transport. The next one is carrier protein mediated. And carrier protein mediated diffusion. The carrier protein, we talk about it like a revolving door. Um, and this is because when you walk through a revolving door, you go in and it's only open to you on one side. It's not like both sides of the door open at the same time. So you go in and then you walk around and then you can go out the other side. Right. So the channel can only be open to one side at a time. So if this was the channel like that, and it's open to this side at first, and it loads an ion, then oh, that's a really big gap. Sorry. Then it would spin and release the ion into the cell like that. So these are also very molecule specific. They also can recognize molecules based on charge, size, polarity, those kinds of things. Examples of carrier proteins that we need to know are the glucose carrier proteins. Um, we know of 1 through 12. An important one is that the fourth one is insulin dependent. So it needs insulin to function properly. Something that's important about all of these carrier mediated transport and channel mediated and carrier protein mediated is that are they can become saturated. So if this is the concentration and this is the rate of the reaction, they will increase. The rate will increase with concentration until we reach saturation, and then it will level out. This is saturation. And this happens because there are only so many channels or so many carrier proteins per cell or per membrane. And once those have been filled, we can't move it any faster or fill it anymore. So it becomes saturated and the rate will not speed up. It's not like simple diffusion where it can continue to go faster and faster and faster as the concentration gets faster or gets higher. Um, and then the last type of protein mediated transport is active transport. And this has two kinds of transport. So this technically is two. But primary active transport, this is ATP dependent directly. So it uses ATP directly. It pushes molecules against their gradient. So all molecules move against their gradient. I guess I forgot to mention that in diffusion, all of these molecules are moving with their gradient. So in channel-mediated transport and carrier protein-mediated transport, all the molecules are moving with their concentration gradient. They're moving high to low. In active transport, we're pushing molecules against their gradient. So all their molecules move against the gradient. An example of primary active transport is the sodium-potassium pump. This is an example of an antiport because we're pushing sodium out of the cell, three of them, and two potassium into the cell. So it's an antiport because the ions are going opposite directions. The other kind of active transport is secondary active transport. And in secondary active transport, we are not directly using ATP. However, it's still active transport because it relies on the kinetic energy that we're creating basically from pumping molecules using ATP. So this relies indirectly on ATP. Um, Usually it's going to rely on the sodium gradient. So the fact that sodium wants to go back into the cell because it has a higher concentration out of the cell due to the sodium potassium pump. But secondary active transport just happens when one molecule is moving with the gradient and one molecule is moving with against it. So one molecule is moving with, right? So we could be pumping one molecule of sodium, or not pumping, but diffusing, one molecule of sodium into the cell and another one out of the cell. So something could be going in, and that will push a different molecule out against its gradient. So if we're pumping sodium in with its gradient, we could be pumping a protein out against its gradient. This is another example of an antiport. And this could also happen with a symport. And that would be if they're both going the same direction. So if the sodium is going in and say we're pumping glucose in as well, that is an example of a symport. Okay, so for osmosis and tonicity, um, osmosis is basically just the diffusion of water. So simple diffusion is just molecules moving with their concentration gradient from high to low without using anything crazy. Osmosis is very similar. It just uses an aquaporin. So water is diffusing using an aquaporin. So it's moving high to low using an aquaporin. A lot of times when we're talking about osmosis, water also follows solute. So water follows solute. And that'll be important when tonicity comes into play. Um, how does osmolarity differ from molarity? So osmolarity is a measure that we use to describe the amount of particles in a solution. So osmolarity, the definition is particles per liter of solute. And molarity is, by definition, moles per liter of solute. So this could be different for something like, say, sodium chloride. So for sodium chloride, a 1 molar solution, so a 1 molar solution of sodium chloride would actually be 2 moles or 2 osmoles or have a 2 osmolarity because sodium chloride dissociates into sodium and chlorine or chloride when in water. So you have 2 particles for each um, sodium chloride that you put into that water. So for each mole of sodium chloride, you have 2 moles of particles. So your osmolarity would be 2, where your molarity would be 1. And that's kind of how osmolarity and molarity differ. They're not always the same number, but if something is insoluble, they would be the same number. Um, and then, so to kind of describe osmolarity and tonicity, I'm just going to draw this out like this. So this is going to help me describe osmolarity. And then I'm going to do it underneath so that I can keep it, oh, sorry, a little bit stable here. This is going to help me describe tonicity. So while osmolarity is just a measure of particles per liter, and with osmolarity we can compare two things to each other. So for example, this could be the solution, right? And then a cell. With tonicity, we are going to measure the effect of the solution on the cell. What happens when we put the cell in the solution? So, tonicity is the effect of the solution on the cell. Osmolarity is just comparing concentrations, basically. So if we have, say, a 0.9% saline solution, that's 300 milliosmol, and our cell also is 300 milliosmol. So when we put them together, we have 4 dots in the solution, representing 300 milliosmol, and 4 dots in the cell. So there would be no net movement, which would be an isotonic solution. Since these 4 dots are also equal in the osmolarity, it would be an isoosmotic solution. However, if we had, so that's a 0.9% saline solution. If we had a 5% dextrose solution, that also is 300 milliosmolar. So if we put them together, again, you would just have 4 dots. So it'd be isotonic and isoosmotic. But if you put, that shouldn't be there. If you put the 0.9% saline plus 5% dextrose, you would have a 600 milliosmolar solution. In your beaker, and a 300 milliosmolar solution in your cell. That is no longer an isoosmotic solution. That's now a hyperton or a hyperosmotic solution because you have more a hyperosmotic solution as compared to the cell because you have more solute in the solution than you do in the cell. So what's going to happen when you put the cell in it is the dextrose is going to move into the cell, 2 molecules at first, because it wants to diffuse. It only thinks about itself. It wants to diffuse and make its concentration equal to itself on the outside. But dextrose is really special because it gets metabolized by the cell. So that dextrose just goes away. And then that would happen with this molecule, and then again with this molecule. And so we end up with an isotonic solution, even though we had a hyperosmotic solution. Another way that a solution could affect a cell is if we had a urea solution. Just gonna connect that. And you can have a urea solution that's 300 milliosmolar, and that would be isotonic. But urea is also a penetrating particle. And so urea would move into the cell because it thinks about itself and it wants to be equal on the inside and outside of the cell. So it would move into the cell and it would create a hypotonic solution as compared to the cell. It would cause the cell to swell because water would follow the solute. And so the cell would get bigger. And if there was enough urea, the cell would eventually burst.